Good morning, professors. Before I start my presentation, I would like to thank you all for giving me such a valuable opportunity to take part in this defense session. My research topic is on the Basal problem, generalizations to other power series. The aim of this investigation is to give a new proof to the famous Basal problem and discuss some generalizations of it. In this presentation, I will show a way to evaluate Theta 2 and Theta 4 and show that the same method can be used to determine the closed form of other power series. The main results obtained are shown on the slide. Assume that the answer to the Basal problem is C. Then define S to S for any set of complex number as S, which is definition 2.1. Directly by the definition, we have S to A equals to C, where A is a set of non-zero integers. Therefore, to find C, we just need to find S to A. Now the question is how to find S to A. A video of 3 blue 1 brown uses the concept of the brightness of lighthouses placed uniformly on a circle, which matches our definition of S2 by the inverse square law. By using the inverse Pythagoras theorem, Grant Sanderson, the creator of this video, finds a family of sets such that the S2 value of those sets are all equal to pi squared over 4, and the sets tend to the sets of odd integers as the size of circle tends to infinity. Inspired by the video, we will consider a similar family of sets such that the S2 value of them tends to pi squared over 6, and the set tends to A as the size of circle tends to infinity. To be precise, we have definitions 2.2 and 2.3 on the slide. At the beginning, alpha j are uniformly distributed along the circle with radius k over 2 pi. And as k increases, so does the size of the circle. We can see that the alpha j's are getting close to the real axis. By the uniformity of the points, the horizontal distance between adjacent points will tend to 1. This motivates us that for such family of sets AK, as k tends to infinity, S2AK will tend to S2A. To show that this is really true, we first introduce a few lemmas, 2.4 to 2.6. Relates sign of argument of alpha j and the modulus of alpha j. 2.5 establishes a bound on the partial sum of the required series. 2.6 establishes a bound on 1 over sine squared x minus 1 over x squared. Next, we have lemmas 2.7 to 2.9. At the first glance, it may seem like the bounds out of nowhere, but we can actually see that combining all these 3 lemmas can prove that as k tends to infinity, S2AK tends to S2A. The proof of lemma 2.7 is the most complicated. It involves of 2.4, 2.5, 2.6, cosine rule, and Cauchy-Schwarz inequality. Then we move on to 2.8. The key to the proof is to justify that x over sine x is less than or equal to pi over 2 for x between 0 and pi over 2, which involves some calculus. As for 2.9, the scale used is similar to that in 2.5. Here's lemma 2.10. By combining 2.7, 2.8, 2.9, and together with the triangle inequality, we have our desired result. After obtaining the key step to our solution, it remains for us to find a formula for S2AK and take the limit when k tends to infinity. The proof of this lemma relies heavily on the Vieta's formula. As the alpha j's we have been considering are roots to a certain polynomial, we express the sum of squares of the reciprocals in terms of the coefficients of the constant polynomial. Hence, we have a closed form for S2AK. Therefore, S2C equals S2A equals pi squared over 3 and c equals pi squared over 6, which is the solution to the Basal problem. Now we will look for some generalization of the Basal problem, which can be proved using a similar method. I'm going to show this by finding Theta 4. To find Theta 4, we first have definition 3.1 as shown on the slide. Similarly, we have S4 equals 2 Theta 4. Then similar to 2.10, we can deduce that S4AK tends to S4A as k tends to infinity. Now it's left to find a formula for S4AK. We have lemma 3.2 as shown on the slide. And the equation above, at the end we have Theta 4 equals pi to the power 4 over 90, as expected. As a remark before we move on, note that for any k-1 variables, and for any positive integer n, the sum of the nth powers can be written as a combination of powers of elementary symmetric polynomials of those variables. We can actually use the similar analysis argument to compute theta to n. However, the complexity of such computation is extremely high, so we skip this part and move on to other types of power series. Nevertheless, we know such sums are computable with such method. Previously, we attempted to generalize the exponent of our series from theta 2. Now we try to generalize the base. That is, we try to calculate the answer of this series for positive real numbers a larger than b. First, we try to find the value when m equals 2. To do this, we do something similar to that when we calculate theta 2. We define beta j to be points uniformly distributed across the circle defined in 4.1, and this time we take all points defined, which includes beta naught, unlike what we did in theta 2. Again, as k increases, so does the size of the circle. The beta j's will get closer to the real axis, with horizontal distance tends to a. Using an argument similar to that in previous parts, we have S2bk tends to S2b when k tends to infinity. What remains is to express S2bk in terms of a, b, and k. The desired expression is shown on the slide. The proof uses the same idea in the proof of lemma 2.11, which is the Vieta's formula, but that's a bit different in the part that we find the polynomial with roots being elements in bk. And so eventually, S2b equals 4 pi squared z over a squared 1 minus z whole squared. But this is not the answer we want here, as we do not expect the final form to contain z. Notice that although z is a complex number, as the whole fraction is real, we can write the given expression to be equal to its modulus. Then some algebra gives the answer, which is pi squared over a squared sine squared b over a pi. Of course, we can just move on to higher even powers like what we did in theta n. But the difference between the current setup and the previous one is that there's now no symmetry about the origin of the limiting case, where everything converges to the real axis. So that makes odd power cases meaningful. Hence, we consider the case m equals 3 as an example. S3 is defined similarly. Again, we have S3bk tends to S3b when k tends to infinity. Then doing similar calculations, we have lemma 4.4 as shown. Doing limits again, S3b equals 4 pi cube I z times z plus 1 over a cube 1 minus z whole cube. Again, as S3b is real, we can again equate it with its modulus, and eventually we have the required answer to be pi cube cosine b over a pi over a cube sine cube b over a pi. We can actually use the similar analysis argument to compute this series for any positive integer m. These two results allow us to determine the sum in closed form for all powers m. However, the complexity of such computations is again extremely high, so this part is omitted as well. Nevertheless, we know such sums are computable with such method. Towards the end of the presentation, allow me to share a bit about theta 3. Finding the value of theta 3 is a very well-known open problem. In fact, Theorem 1.4 has a close relation with theta 3. For example, when a equals 3 and b equals 1 in Theorem 1.4, we have the series shown on the slide to be equal to 4 root 3 over pi cube times pi cube over 2 for 3.